Good day, everyone. We are Lishov Dmitry and Rolov Denis, and we would like to present you our HPPL course final project, which is Schelling's model in 3D. Schelling's model of segregation is an agent-based model developed by an economist, Thomas Schelling, in the 1970s. At that time, the phenomenon of the ghetto was widespread in the United States, and Schelling watched this process, and as a result, it came to the conclusion that different areas are formed not because of the general enmity of people of different race, but because a person prefers a place of residence where his neighbors will be similar to himself. As a result, everyone settles next to their own kind and everyone is happy. So his model doesn't include outside factors that place pressure on edges to segregate, but does demonstrate that having people with mild in-group preferences towards their own group could still lead to a highly segregated society via de facto segregation. We already had a bit of experience working with this model during our course, and here you can see few GIFs of this project with different values of parameter R. But we decided to investigate this problem further and expand Schelling's model to 3D case, because we wanted to study more about 3D plotting in Python and also explore how and if Schelling's model will work in 3D case. So a little bit about code structure. As we wanted our code to work fast, we decided to implement our model via matrices. We initialized the playing field with which consists of the same amount of zeros and ones, where ones are the first group cells and zeros are the second group cells. Another speed-up feature which we wanted to use is already implemented convolution. So we use this technique to calculate the number of neighbors around the current point in 3D space. For this, we merely used a 3D kernel with ones padding and 0 in the center of our imaginary cube. We had two 3D matrices, original and inverse, and for each one we applied kernel as a window function and then merged these fields into the one. Then any cell which is okay with its percentage of neighbors were not shuffled and other were shuffled. As a result, we get these 3D GIFs you can see on the slide, and the first slide will show you GIF for R equal to 0.375. We can see that in the beginning there are a few permutations, and then the situation became stable because the value of R is quite small. Then we would like to show you the result for R equal to 0.7. And here you can see that after about 50 iterations, we start to see some clusters appearing on the slide, and after about 100 operations we can see good segregated blue and white cells, both in 3D case and in our projections case, which you can see on the right of the slide. And we also implemented we also ran our code for R equal to 1, and you can see that it is just random moving of people because they will never be satisfied with their neighbors. Also, we made a plot of number of households that want to move during the time, and you can see that when the value is less or equal than 0.75, there are some declines in the graph in the number of people who want to move, and then they became stable. And for the higher values, as 7, 8, and 1, we see that from the very beginning there are the same amount of people who want to move. We also investigated the ways to parallelize our code, and the first idea was to use QPy instead of NumPy. Unfortunately, signal.convolve didn't work on collab with QPy, but we used another convolve from ND image library, and on the screen you can see the resulting plot of comparing computational time of NumPy and QPy. And you can see that in the beginning, when we took the matrix 10 by 10 by 10, the value of time was quite the same, but with increasing the value of dimension, we see that QPy shows quite better result than NumPy. There are also ways to make this code parallel, and we think that it is also possible using multiprocessing. It will be quite similar to the 2D case. We can split our cube into parallelepipeds and send receive lower and upper layers to the neighboring processes and then gather it all together. However, we will need to do it on every iteration, so it is possible that gathering on every step could be 2 times expensive and there will be no speed involved. Also, if we rewrite the convolution by hand and if we a little bit change our initial code, we could also use Numba to speed up our course, and I guess it will work quite well too. So that's all we wanted to tell you about our project. We are free to answer any of your questions. Thanks for your attention.